Welcome to this presentation. My name is Göttel from University of Neuchâtel and I will present you Scrooge attack, undervolting ARM processors for profit. This work was done in collaboration with Konstantinos Parasyris from Lawrence Livermore National Laboratory in the USA, Osman Unsal from Barcelona Supercomputing Center in Spain, Pascal Felber, Marcelo Pasin and Valerio Schiavoni from University of Neuchâtel, Switzerland. Let me begin with the introduction. Today's cloud market is seeing an expanding share of ARM-based instances. This is because of the announcement of the ARM Neoverse microarchitecture. Before the Neoverse architecture existed, server platform providers had to use custom-developed processors or repurpose application-grade processors in order to provide an ARM-based server-grade platform. Examples of such processors are the Ampere eMac, AWS Graviton, and Marvell ThunderX. Microprocessors have the problem that they have a conservative voltage margin which is due to process variation. In this case, the processor manufacturer considers a worst-case outcome of the batch and adjusts voltage and frequency settings accordingly. To compensate for this voltage margin, there exist power management mechanisms. In our scenario, we envision a Scrooge cloud provider which undervolts the cloud infrastructure for profit. Let me open a parenthesis. What is undervolting? Undervolting is a technique that decreases the supply voltage of a processor below nominal value. This is primarily done in order to conserve power. On the right hand side you see a plot in which you have three systems. The orange and blue system make use of undervolting and can be between 5 to 12% more energy efficient. The red system, however, is barely using any undervolting and therefore remains unchanged. Undervolting can also reduce the core aging. It has the advantage that it maintains the performance of the processor. However, it comes at the cost of reliability. This is because of the introduction of errors due to timing violations. In our work, we want to analyze the consequences of undervolting from the point of view of a cloud user and a cloud provider. Of course, a malicious cloud user could also exploit the undervolted state of an instance, but we consider this out of scope of our work. We just mentioned Plundervolt and VoltPwn as two undervolting attacks against trusted execution environments such as Intel XJX, which can also be found in cloud instances. We have developed a detection method in order to identify such undervolted instances. The cloud user will crash these instances such that the cloud user is covered by the service license agreement. Under our strict threat model, this is the only way to prove the existence of such undervolted instances. The detection method makes use of heat dissipation by adjusting the processor's load and its operating points. This is because temperature has always been a major issue for microprocessors. Finally, our detection method is a non-selective fault injection method. So to summarize, what are the research questions of our work? First, what is necessary for a malicious cloud provider in order to pull off a stealthy undervolting strategy? And second, does a cloud user have the ability to uncover such an undervolting strategy? ARM processors are low power processors by design, and we emphasize this with the following benchmark. On the left hand side you have a CPU bound workload, and on the right hand side you have a memory bound workload. To the left of the plot you find ARM devices, and to the right you find x86 server grade devices. For the CPU bound workload we see that the energy consumption is fairly comparable. For example, 26 up to 122% less energy efficient than the AMD EPYC microarchitecture, or 60% more and 7% less energy efficient than an Intel Kaby Lake microarchitecture. However, the picture is completely different for a memory bound workload. In this case, we have a huge performance gap. Notice the logarithmic scale. The memory-bound workload difference is due to the low-power DDR memory performance of our ARM devices. What power management techniques exist? Well, there is frequency scaling. Frequency scaling is the dynamic regulation of the frequency of a processor. If you go beyond the nominal frequency, it's called overclocking. If you go below, it's called underclocking. Frequency scaling is used in order to conserve power, but it can also reduce the heat dissipation. This is typically used with firmware throttling the CPU in order to bring back its temperature to an acceptable value. Voltage scaling is a so-called open-loop system in which an external setting specifies the voltages. This can be, for example, in firmware or in a BIOS. Voltage scaling influences the charging and discharging rate of capacitances in the processor and therefore its frequency. If you combine these two scaling techniques, you obtain dynamic voltage and frequency scaling, which is the simultaneous software-controlled voltage and frequency regulation. This is defined by so-called operating performance points, which the processor manufacturer defines as pairs of frequency and voltage in order to guarantee correct execution of instructions. Finally, there is adaptive voltage scaling, which is featured in our devices of choice. It is a so-called closed-loop system in which a feedback loop of sensor data regulates the system. This sensor data can, for example, be the current voltage level, the frequency, or the load of the processor. And based on this sensor data, the system adjusts the voltage level. AVS can also account for process variation and aging. Now, our platform of choice is the Raspberry Pi. The Raspberry Pi has a ARM Cortex application-grade processor, a Broadcom video core GPU. Our devices have between 1 and 4 GB of low-power DDR memory, and they are equipped with a micro SD card for non-volatile storage. The voltage is adjustable in 25 mV steps, which you see on the bottom left. When booting up, the system, or AVS in this case, will determine the nominal voltage, which is level 0. A user can then apply an offset level, for example level 1, in which case plus 25 mV is applied. Or the user can also undervolt the system, for example with level 2, in which case a minus 50 mV will be applied. At the time of writing, the 4B had no undervolting support. And to summarize, we are using the Raspberry Pis in order to mimic server-grade ARM instances. So what is necessary for a cloud provider in order to guarantee a stealthy configuration? Let's assume that the cloud user has deployed an undervolted instance. During the boot up, we need to exchange the undervolted configuration for a nominal configuration. Otherwise, the cloud user will immediately identify such an undervolted instance. When the system is shut down, then again we need to exchange back the nominal configuration for the undervolted configuration. Otherwise, on the next startup, the system won't be undervolted. The same applies also during a reboot. In our threat model, we consider that the cloud provider has physical access to instances and can also intercept firmware requests, such as, for example, voltage and temperature readings. So if the cloud user issues a voltage or temperature reading, the firmware will intercept the reading, nevertheless forward it to the hardware, get back an undervolted value, for example, substitute this undervolted voltage value by some nominal plausible value, and return it back to the user. This means that the cloud user cannot trust any voltage or temperature readings on the instance. Now, how can you deploy such a setup? In our case, we used 3 Raspberry Pi models, the 3B, the 3B Plus, and the 4B. We use an Alcium PowerSpy 2 power meter to measure the power consumption, a network-enabled power strip in case we need to power cycle the Raspberry Pi, a UART to USB cable in order to monitor the boot up process of the Raspberry Pi, a Bluetooth dongle in order to retrieve the power measurements from the PowerSpy 2, and an auxiliary machine in order to deploy and monitor our setup. The first step of a cloud provider is to determine the undervolting level, and this can be done with a temperature-based Guardband analysis. What is the procedure? Well, we start with at nominal voltage with some benchmark. If the benchmark runs successfully, then we lower the voltage configuration, reboot the system to apply the voltage configuration, and rerun the benchmark. And we repeat this procedure until the benchmark crashes or the system no longer boots up. This way we obtained the following 3 Guardband analyses. For the Raspberry Pi 3B, we see that the nominal voltage is slightly increasing. This is a result of the AVS system adjusting the voltage based on the increasing temperature. For the Raspberry Pi 3B Plus, we see a voltage drop, which is the result of the firmware throttling the processor. And the Raspberry Pi 4B has no undervolting support at all. Now, what could be a benchmark of choice for a cloud provider? Well, it could be, for example, StressNG. Here you see 16 stressors out of 169 that we have evaluated. On the top, you find stressors that have been deployed on an actively cooled Raspberry Pi, and on the bottom, a passively cooled Raspberry Pi. The darker the shade of the cell, the more energy efficient the stressor was executing. In general, we can say that active cooling actively cooled stressors run more energy efficiently than passively cooled stressors. However, none of the stressors manage to crash an undervolted instance, which means that they don't apply the necessary stress on the system in order to crash an instance. Therefore, benchmarks such as StressNG are not ideal, and other stressors such as power viruses should be used in order to correctly determine the guardband of a undervolted instance. Therefore, we have developed our own benchmark, which is a multiplication benchmark. From the cloud user's perspective, we have done something very similar to a Guardband analysis, in which we deployed our benchmark 741 times on undervolted to determine the voltage and frequency levels of these platforms, and of these 265 measurements failed. Now, that said, none of the 700 measurements had at any time an incorrect product as a result of the multiplication. Therefore, we conclude that the multiplication instruction is not on a timing critical path. The highest crash probability we observed was at 60 degrees. We had 40% on the 3B Plus and 90% on the 3B. The 40% of the 3B Plus is due to the firmware throttling kicking in at 60 degrees. This percentage could be higher. The crash temperature can be decreased if the undervolting is more aggressive. The process failure injection. We injected faults in 30% of the cases. These were user processes. In 15% of the cases, these were kernel processes, and in 51% we could not determine the process because the system crashed before we could access this information. Now, if we combine the undervolted instance with our detection method, then we obtain the following results. Our deployed instances are bare metal instances in the top row and container instances in the bottom row. In the case of bare metal instances, we could crash the instances after about 3 minutes for the Raspberry Pi 3B and 2.5 minutes for the Raspberry Pi 3B Plus. The crash temperature was around 62 degrees Celsius. In the case of container instances, we could already crash instances at after 30 seconds on the 3B and a bit more than 4 minutes on the 3B Plus. Now, in a future work, what we want to achieve is that we want to synchronize these crash points such that we can simultaneously crash the instances in order to guarantee that we are covered by the SLA to prove that the cloud provider has undervolted the instances. So to conclude, we have shown you a novel attack scenario in which a Scrooge cloud provider undervolts the infrastructure for profit. The undervolting can save on average between 5 to 37% in energy. However, the undervolting is susceptible to thermal running. Active cooling has shown to mitigate to some extent the thermal running. However, benchmarks have proven not to be the correct approach for a Guardband analysis. Instead, one should use power viruses in order to determine the Guardband and have more accurate values. In future work, we want to apply the Scrooge attack to actual ARM server grade hardware. We also want to include virtual machines in our evaluation, and we want to develop a detection method that can simultaneously crash instances as presented on the previous slide. And finally, the entire dataset of this work is available on my GitHub page. And with that, I want to thank you for your attention.